And so I'm going to talk about things I've done during my PhD. A good part of what I did will be presented here. Sorry, lower, like that. Is it okay? So I will talk about a notion of uniform strategies. And so first I will try to give motivation for introducing this notion. Try to show examples of strategies where you have constraints on unrelated plays that you want to enforce on the strategies in the game. Then I will define our notion of uniform strategies. And then I will present the results we have on the problem of deciding the existence and synthesizing uniform strategies. And then I will briefly conclude. So first, the context is that of two-player turn-based games played on finite graphs. So simple framework. And we consider the problem of the existence of a winning strategy, so classic problem. So usually when you have a game, you define the winning condition on individual plays. On each play, you say whether it's winning or not. You have many different ways of defining the winning condition, reachability, safety, parity, etc. But in some cases, some types of games, you want to add properties on your strategies that cannot be evaluated on single plays, but rather have to consider sets of related plays. So it's kind of second-order properties on the strategies you want to look for in your game. So I will give 3 examples of such second-order properties. So the first one is in games with imperfect information. So just for the moment, without imperfect information, this is a kind of arenas, like a classic formalism of arenas, where you have positions and you have actions on the arrows. So at the beginning of the game, you're in this initial position, and player 1 will choose an available action. Here, the only possible choice is A. And when player 1 has chosen an action, player 2 will choose an arrow labeled by this action. So here, player 2 can choose to go here in V1 or in V2. And then again, so let's say player 2 chooses to go here. Then player 1 will choose an available action. Here he can choose between A or B. Let's say he chooses B, then player 2 can choose between staying in V1 with this loop or going to V2. And now let's say that we consider safety objective. So the red positions are bad positions. And player 1 wants to avoid ever reaching a bad position. So if it's a game with perfect information, it's easy to see that player 1 can have a winning strategy. It's just that if player 1 is, if the game is here, player 1 plays B, and if it's here, player 1 plays A. Easy, you will never reach these bad positions. But then if you add imperfect information, so here I represent the information with colors. So player 1 now no longer observes positions, but just the colors of positions. So for example, it doesn't make the difference between V1 and V2. And so the natural assumption when you have this imperfect information is that player 1 cannot plan to play differently in positions that he does not distinguish. because like he cannot say here I play B and here I play A because he doesn't know where he is when he's playing. And so here, if you add this constraint, you no longer have a winning strategy for player 1 because after the first move, he has to play, he doesn't know whether he is here or here, and he has to play the same action in both cases. If this action is A, then he loses when player 2 has chosen to go here. No, I said A or B? No, if the action is A, then he loses if player 2 goes here, and if it's B, he loses in this case. So there is no longer a winning strategy. So you see that this constraint changes many things in solving games. As soon as you have imperfect information, you have so this relation between plays that player 1 cannot distinguish. And because of this constraint on strategies that is often called observation-based strategies or imperfect information strategies or even uniform strategies sometimes, this constraint changes the nature of the game and the results and the existence of strategies and the complexity of deciding this. And this is not this is a property of strategies that you cannot evaluate on single plays. You mean to consider all the related outcomes to check whether the strategy really plays uniformly in indistinguishable situation. So it's some kind of second order property, if you want. Now a second example comes from so-called logics of imperfect information, which are basically first order logic in which you add special additional atomic formulas that come from dependency database theory usually, and they have the particularity that they need, in order to have to make sense, they need to be evaluated not on individual assignments for variables like in first order logics, but in sets of assignments, which are called teams usually. So here X is a team and S is an assignment in the team. For example, dependence logic, which is maybe the most well-known example of such logics with independence-friendly logic. So in this logic, the additional atomic formulas that you add are of this form. So X and Y are variables, and this says that Y depends on X, or more precisely, the meaning would be that the value of Y is completely determined by the value of X, or the value of Y depends only on the value of X. And so because you want to evaluate some dependence between the values of variables, or more generally dependence between objects, you cannot evaluate it on a single assignment. You have to see how the value of Y changes when the value of X changes. So you need to consider several assignments at the same time. And for example, if your team is made of two assignments, S1 and S2, this team will verify this atomic formula if whenever, like two assignments give the same value to X, then they also give the same value to Y. So this tries to capture the idea that the value of Y is determined by the one of X. When X has the same value, Y also has the same value. And of course, if you evaluate it on a single assignment, it doesn't make much sense. If you evaluate it on a big set of assignments, then if it's true on a big set of assignments, the chances are that Y really depends on X. So then, like in first order logic, you can give the semantics with a game between two players, verifier and spoiler. Verifier who tries to prove the formula true in a given model, and a spoiler who tries to prove it false. But we'll see that you have to add additional constraints and strategies for it to work on dependency logic. So I remind quickly how it works for first order logic. So you have positions of this form where, so I take a formula of dependency logic and a model or first order here. So here is a subformula of the big formula. This is an assignment for variables. And this is one of the two players, verifier or spoiler, who is currently in charge. So it starts in this position. And the moves are like for first order logic. So in a disjunction, the player in charge chooses the disjunct. For an existential quantification, the player in charge chooses a value for x. And when there's a negation, you switch players. And then you have to... So of course, all plays are finite because you decompose the formula and you reach an atomic formula. And you have to say which terminal positions are winning for whom. So if it's a formula of this kind, then it's winning for the player currently in charge if this is true in the model with the current assignment. The same for a relation. But the problem is that when you want to add dependency atoms for dependence logic, then here, in such a terminal position, you cannot define who wins in this position. Because as we saw, you cannot define the semantics of this formula in a single assignment. So in order to give the semantics of these atomic formulas, you have to consider all the terminal positions of this form that you reach with a given strategy and evaluate this formula on the set of assignments that you reach with a given strategy. So again, this gives in order for your game semantics to be correct with regard to the Tarski style semantics, you need to put a constraint on strategies player one is allowed to use. And this constraint, again, involves sets of related plays. Here, related plays would be those that end up in the same atomic dependence formula. In the case of imperfect information, related plays were indistinguishable plays. So yet another example of game where you want to consider several plays in order to say who wins. It's when your winning condition involves knowledge, epistemic aspects. I forgot to talk about this. So I just talked about the example of dependence logic, but I said there are many other kinds of logics of imperfect information where you had different atomic formulas that come all from database dependency theory, and they all have such kind of semantic games with additional constraints on strategies. And Gradle recently defined a notion of second-order reachability games in order to try to study at once the properties of all these particular games that they obtain by adding these ad hoc constraints and strategies for capturing the semantics of the various atomic formulas. And there he uses something called consistency criteria, which will be an instance of what we call uniformity. So now, as I had started to say, if you consider games where the winning condition involves knowledge, then in order to evaluate the knowledge, you have to look at related plays also. So it's also some kind of second order property on the strategies. So for example, so a simple example that we call games with opacity condition. So you have an imperfect information arena, like I've shown at the beginning, where some positions are considered secret. And the aim of player one is to prevent player two from ever getting perfect knowledge of the secret. Like player 1 wants to make sure that player 2 is never sure that the current position is a secret one. And so, in order to evaluate whether player 1 wins a play, you have to consider the plays that player 2 does not distinguish from the current one to evaluate his knowledge. So, in this case, it's the winning condition itself that is a constraint involving sets of related plays. So now we see that in a number of cases you want to deal with strategies that have properties that involve sets of plays related by some means. And you have many kinds of relations between plays that you may want to consider. So for epistemic aspects like games with imperfect information or games with epistemic winning condition, the relation will represent the plays that a player cannot distinguish from, but the nature of this relation will depend on the assumptions you make on the player's ability, like does he remember everything from the beginning, or does he remember nothing and just sees the last position? Does he perceive things synchronously or asynchronously? Well, this gives rise to a number of different relations. For logics of imperfect information, the relations just depend on what kind of atomic formulas you have in your logic. And so what we propose to do, because apparently it has not been studied in its generality, this notion of strategies with second order properties. And what we want to do is to study this notion and to allow for a large class of relations, because we see that many kinds of relations can arise from different needs, and so we want to try to be as general as possible and see what we can get being as general as possible. So here we have the three examples we have talked about, and so we define a notion of uniform strategies that capture this. And in fact, in games with epistemic winning condition, you can capture many known problems from the literature, like games for non-interference or diagnosis or opacity and things like that. So now I will define what we call uniform strategies. So we consider simple two-player turn-based game arenas without actions on the arrows. It's just, so circles here belong to player 1 and squares belong to player 2, and we put information in the position with some atomic propositions. So in a game you have a finite set of positions split between those of player 1 and those of player 2. You have moves, initial position, and evaluation on the positions. Then a few notations, but I'm not even sure I will need this because I'll try to be very informal. But just you have infinite plays. Yeah, we assume that all plays are infinite. There's no blocking position. And a strategy for player 1 is a mapping that says in any finite play that ends in a position where it's his turn to play, what next position he should choose. Of course, a position reachable from the current one. And so we do not talk about winning condition for the moment. It's just you have an arena, and then we will define properties that you want on the strategies you...
Yeah, but to strategize, you need to know objectives.
The objective will be to find a strategy that verifies the property.
Oh, it's yours, I'm saying. Player's strategy is to win something. So,
well, you can put it in the uniformity requirement. But for the moment, there's no winning condition. The only requirements we put on strategies, we put in our language, in the formula we will choose. And the only problem we'll consider is to find a strategy that verifies the property we want. And so we specify these properties that we call uniformity properties in our language. That is just CTL star. for temporal properties of strategies. So CTL star, because we will see strategies as trees. I will show just in a few slides. And we have two special quantifiers, these ones, that are used to grab sets of plays, of related plays. The first one, that we call the strict quantifier, so this means that phi holds in all related plays in the strategy. All formulas will be evaluated in a given strategy, and this means that you quantify over all related plays, but only in the strategy. This one, the full quantifier, means that phi holds in all related plays in the game, not only in the current strategy under evaluation. We'll see why we may want to use this. And so the syntax is just CTL star with these additional state formulas. Sorry? No, it's just any, you just take a relation, a binary relation on place for the moment. I'll say that just on the next slide for semantics. But just as I said, we see strategies as trees. So here, so the big tree represents the unfolding of some game arena. So it can be infinite in general. Well, we consider only infinite plays, so it is an infinite tree. And a strategy tree is a subtree of this unfolding, where every time its player wants turn to play, you just keep one child. So this represents a strategy for player one. And so we'll evaluate our formulas on such a strategy tree. So for the semantics, we need a universe that will represent the set of all possible plays in the game. So the big tree, the big unfolding. In order to give a meaning to related plays, we take a binary relation over the finite plays. It can represent knowledge, beliefs, imperfect observation. It can be something that's not really related to information, like in the game semantics for dependency logic and things like that. It can be any relation you want to use for some motivation. And you take a tree and you evaluate a formula in a universe, a relation, and a tree. And the semantics is just as for CTL star, except for these two quantifiers. I don't give the formal semantics, I just give the intuition on this small example. So here you have like the universe in black, like here also, and a strategy tree in yellow. The blue arrows represent the relation between plays. So this play is related to this one, and it's also related to this one. Notice that the relations we take are not necessarily equivalence relations in general. And so let's say that you want to evaluate this formula at this point of this strategy tree. So here, because you use the strict quantifier, you only quantify over related plays in the strategy. So here, for this formula to be true, phi only needs to be true here, in the related play that belongs to the strategy. This play is related to this one, but it's not in the strategy, so you don't need to evaluate phi there. With the full quantifier, you quantify over all related plays, even those that do not follow the strategy you are considering. So here, for these to hold here, phi must hold here and also here, even though this is not in the strategy you are considering. So a few examples of what you can say with that. So for imperfect information strategies, so we'll take, well, I should have said we take as relation between plays the observational relation for player 1. So this, the indistinguishability relation between plays. And this formula means that at all points, so this is evaluated in a strategy tree. At all points, when it's your turn to play, there is one move that in all related plays in the strategy, like you play this move. So in all indistinguishable plays, you play the same move. So here I have to put for all, but I could have put exists. It's indifferent because there is only one child in position where it's player 1's turn to play. So here for all or exists would be the same. But you have to put something because otherwise it's no longer a formula of our language. But anyway, it's not important. So this means that the strategy is observation-based. When it's my turn to play, there is one move that I play in all indistinguishable plays of the strategy. But here, of course, you want to quantify only over the plays in the strategy. You don't want to say that in all plays in the game, there is only the same move everywhere, because you can have several possible moves. But for example, if you consider, the games with opacity condition I mentioned earlier. So remember, you have some positions that denote a secret information, and player 1 wants to prevent player 2 from discovering. Yes?
When it's information sets, right, it's clear to me that if I make a move M1, because information sets are all nodes where I have control, the player has control.
Yes.
So if for uniform strategy, I want if I make a move M here, I must make a move M there.
Yes.
But if I'm looking at an arbitrary relation, right, I don't even have control over the other one. Right? I mean, you could be relating nodes where one of which I have control and the other one I don't have control.
Yes.
But then this modality, this box, isn't it?
Yes.
Might want me to make a move there as well, right?
Yes, but here I consider the classic case where you consider like the relation you choose here to give the semantics will be, for example, perfect recall and all related plays.
Yeah.
It's okay. But of course, if you take any like a random relation, then it will no longer make any sense. Yeah. It depends on what you want to capture, what kind of property you want to capture. So for games with opacity conditions, so player 1 wants to prevent player 2 from knowing for sure that the current position is a secret. So then you take this relation to be player 2's observation relation, and you take this formula that says that always it's not the case that player 2 knows the secret. So there is always one indistinguishable play that doesn't end in a secret position. And this time, why do you want to use the full quantifier? Because player 2 does not have to know what is your strategy. So player 2, he observes a play, and there are plays that are indistinguishable to him, but he doesn't know what is your strategy, because it's your strategy. You didn't tell him what is your strategy. So there may be plays that he thinks are possible, but that do not follow your strategy, but still he considers them possible, so you have to take them into account to evaluate his knowledge. So then you have to use the full quantifier. So in order to capture, for example, observation-based strategies, you use the strict quantifier. For the coherent strategies of dependence logics, etc., you use the strict quantifier also. But in epistemic winning condition, if the agent that the agent whom you consider the knowledge of knows the strategy you want to use the strict quantifier. If he ignores the strategy, you want to use the full quantifier. So now, so given an arena, a relation, a binary relation between plays in a formula, you take as universe the set of all possible plays, and you say that a strategy is phi uniform if the strategy tree, I forgot to put the relation here, but if the strategy tree for sigma verifies phi in the universe U. And the problem that we want to consider is the existence of a uniform strategy for player 1. But of course, if you want to consider this as a decision problem, you need to represent your relations finitely. So we decided to consider the class of rational relations that are relations that can be represented finitely by means of finite state transducers. So they are recognized by finite machines. And so this is an example of a finite state transducer. So it has two tapes, and it reads two words, not necessarily synchronously. You can read faster on one tape than on the second one, and etc. And when it has finished reading the two words, it decides whether they are related or not. So for example, here, this transducer recognizes the relation. So it will accept two words if they have the same number of A's. So what does it do? As long as, so it reads all the B's it can. When it reads an A on the, no, let's say that, when it reads an A on the first tape, it goes here, and it reads the second tape until it finds an A also, and then it comes back here. Same if it finds an A on the second tape, it waits until it finds one on the first tape, etc. So it can recognize many kinds of relations. So a relation is rational if and only if it is recognized by a transducer. Regular relations are a subset of rational relations, and there are those that are recognized by synchronous transducer, which means that they can only, like they have to read one letter on both tapes every time. And we also consider the class of recognizable relations, which are they are characterized by the fact that they can be recognized by a finite word automaton in the following fashion. So a relation is recognizable if there is a word automaton whose language is the set of words of this form, where U is related to V, and U bar is the mirror of U. So, well, it also holds if you remove the mirror, but this characterization will be more convenient for us. So basically, there is an automaton that can read one word, and then read the second word, and decide if they are related. So this is less powerful than this, which is less powerful than this. So now I will present what results we have on the problem of deciding the existence of winning strategies and synthesizing them. And to do so, we start by considering both kinds of quantifiers separately. Yes?
So the intention of the U bar tree is that I'll climb up to the root of the tree and come down, right?
Sorry?
The U and V. The intention is, I mean, I can always think of them as tree nodes.
Yes.
And the mirror U, V means I climb to the root and then come down.
Yes, exactly. Well, we'll see it better in a few slides. So we start by, so we split the cases of strict quantifier and full quantifiers because they don't have the same properties and you need to develop different techniques to deal with them. And I start with uniformity properties that only use the strict quantifier and do not use the full quantifier. So we define this language where it's the same language, but you don't use this quantifier, the full one. And you consider this problem, this decision problem, take a finite arena, a finite state transducer that represents a rational relation between plays of the arena, and you take a formula without full quantifier, and you want to decide whether there is a phi uniform strategy for player 1 in J. So if you allow for any rational relation, the problem is easily proved undecidable, because you can easily encode, for example, a distributed strategy problem in games with imperfect information. In fact, these relations are quite powerful. Even with regular equivalence relations, you can encode in the behavior of, so consider the game where you have 3 players, 2 players with imperfect information play against nature, and you want to decide the existence of a distributed strategy of imperfect information for these players, for example, safety objective. You can simulate this problem with one player simulating these 2 guys, and you put a requirement on his strategy that alternates between the 2 original players, because with a transducer, which can be non-deterministic, you alternate between the knowledge of the 2 original players, and so you can encode it easily with only one player. So it's quickly undecidable. But if you restrict to recognizable relations, then the problem is decidable, and I will show how. So the basic idea is this classic automata approach to solve, for example, LTL games or things like that. You build from the arena a tree automaton that accepts strategy trees of player 1. And then you build an automaton that accepts trees that verify phi. I should have removed that. So it accepts trees that verify phi, and then you take the product of both automata and you test for emptiness. The problem is that for classic temporal logics, you know how to build this automaton, but if you have strict quantifiers, you need to show how you build this automaton. And so to do so, we define jumping automata, which extend classic alternating tree automata with the possibility to jump in the input tree, which will capture the semantics of the strict quantifier. So just briefly, reminder on tree automata. So alternating tree automata, they have an infinite tree as input, and so this represents where the automaton is currently. And so they can send copies of themselves in children of the current node. They can send different copies of themselves in the same node, etc. So it can only go down. Then you have two-way tree automata that can do the same, but they can also send copies of themselves to the parent node, so they can go back. And then jumping tree automata, they cannot go up like two-way, but they can go down like alternating tree automata. And in addition, you have the possibility to, in the transition function, to send copies of your automaton in all related nodes of the input tree or in some related node of the input tree. So here, so then the automaton is equipped with a binary relation on words on the alphabet on which it works. So here, let's say that the relation that equips the automaton, it gives these links in this particular input tree. So the automaton can send a copy of itself here, and then continue, and then send a copy of itself there, and continue. And so it's quite easy to see that this behavior enables to capture the semantics of the strict quantifier. And so for every formula without full quantifier, there's a jumping automaton that accepts the set of trees that model the formula. But then you want to decide the emptiness of such automata to solve our problem. So because of this, the emptiness is undecidable for regular equivalence relations, because otherwise the strictly uniform strategy problem would be decidable for this class of relations. But if you consider jumping automata where the relation is recognizable, then you can decide the emptiness, because in fact you can build an equivalent two-way automaton of linear size that simulates this jumping automaton. I will give the idea of how you do that. So you take a jumping automaton and the word automaton that recognizes the relation between nodes of the input tree. And so you build a two-way automaton that simulates this jumping automaton. So how do you do? So as long as the jumping automaton has a normal alternating behavior, doesn't do jumps, you just do the same. But as soon as in the transition of the jumping automaton there is a jump, then the two-way automaton will enter a jump mode, so which will simulate the jump. So it triggers the recognizer B in its initial state, and it starts going back up to the root of the input tree. And at the same time, B reads the labels of the nodes here. And when it reaches the root, it has read the mirror of the node here, right? And then you feed it the special symbol, dash, and then, well, it depends if you have if the jump quantifies over all related nodes or over some related node. Depending on the case, you will start sending copies in all children or in some children non-deterministically. So let's say that it was a existential quantification. So you guess in which direction you send your automaton, and you try to find a related node. And you continue reading the nodes you see in your recognizer B. And for example, when you reach this node, you have read in B, you have read U bar dash V. And if B has reached an accepting state, it means that V is related to U. And then you can terminate your jump section, your jump mode, and resume the normal behavior of A. So that's how you simulate the jumps with a classic two-way automata. And so this gives that you can decide the emptiness of jumping automata when relations are recognizable in exponential time, because the two-way automaton is of size linear of the jumping automaton and the automaton that recognizes the relation. And the non-emptiness of two-way automata is decidable in exponential time. So this gives that when you restrict to recognizable relation, the strictly uniform strategy problem is 2x time complete. Because this automaton is exponential in the size of the formula, this is quadratic, so then when you take the product, it's still exponential in the input, and then deciding the emptiness is exponential. So now about fully uniform strategies, so where you have only full quantifiers and no strict quantifiers. So this is simpler, because the semantics of the quantifier does not depend on the strategy you consider. So you can use bottom-up constructions to eliminate these quantifiers before deciding the existence of a strategy. Because once again, the semantics of this of the full quantifier does not depend on the strategy. You quantify over all related plays in the game, so it's easier. So here again, the problem is this one. The only difference is that you consider formulas without the strict quantifier, only the full quantifier this time. And again, you want to decide the existence of a uniform strategy. And so this time, it's decidable for a class of rational relation, but it's non-elementary. And more precisely, if so D of phi is the nesting of full quantifiers, not alternation, just nesting. If it's bounded by k, then when k is lower than 2, it's 2x time complete, and when it's greater, it's kx time complete. How you do that? From the transducer that recognizes the relation, you build an information set automaton. So what is that? It's a deterministic word automaton that is exponential in the size of the transducer that computes information sets. So in what sense? So information set automaton. There's a question or no? Okay. So when it reads a word, it computes its information set, which is the set of last letters of related words, related in the sense of this transducer. So it's the same idea as information sets in imperfect information games, where information set is the set of last positions of equivalent place. Here, the set of last letters of related words, of words related to W. And so, once you have this information set automaton, you synchronize it with your arena, and then you can eliminate all innermost formulas of this form. And then you iterate every time you do a new power set construction, which gives an elementary procedure. And at the end, you no longer have formulas of this kind, so you obtain just so you evaluate them, of course, and you replace them with.
Maybe you should say that by synchronizing J with AT, you get a new game.
Mm-hmm.
You get a new arena.
Yes, you have a power set arena, in fact, on which you can evaluate this kind of formulas positionally, thanks to the information given by the information set automaton. And so then you evaluate these formulas bottom up, and you replace them by a proposition that says where they hold. But the thing is that in general, you have to do a new power set construction for each nesting depth. And at the end, when you have removed all these formulas, you solve the final CTL star game. So this gives this complexity. But then if you make some more assumptions on the relations, you get better results. So if your relation, so we say that, so this is the classic notion of no miracles considered in epistemic temporal logics usually. So our relation verifies no miracles if whenever two plays are related, or two words are related, then if you continue them with the same thing, they remain related. There's no miracle, like they don't stop being related for no reason. And so if the relations you allow are rational, transitive, Euclidean, and they verify no miracles, then the problem becomes 2x time complete. And the reason is that, in fact, these relations are almost equivalence relations. And with this additional assumption, you have that the information set automaton, when it reads two related plays, it reaches two states that are equivalent in the sense that their information set bisimilar. So when you read when the information set automaton reads two related plays, it reaches two states from which, well, no matter what you read, you will compute the same information sets. Yes? Euclidean? Yeah, you can close the triangle, you know? Like if you have this and this, then you also have this. If this is related to this, and this is related to this, then this is related to this. And so with so transitive and Euclidean, it's almost equivalent, an equivalence relation, except that you have some points that are not reflexive, like they branch to classes, like sets of balloons or things like that. And so in this case, we have that the complexity is is not higher than the one of solving simple games with LTL winning condition, which is quite nice. Furthermore, because most relations, indistinguishability relations you consider in games with imperfect information or epistemic temporal logics, they verify these assumptions. They can be recognized by simple transducers, so there are simple rational relations. And usually, if you consider equivalence relations, they verify that. And this is an assumption that you can make easily, like, it makes sense if you think of epistemic aspects most of the time. So quickly, you can extend the language to deal with several relations. So you have n relations, and to each relation, for each relation you have the corresponding strict and full quantifiers. And when you do that, all the results still hold, like undecidability for strictly uniform strategies, decidability for recognizable relations with the same complexity, for fully uniform strategies. With rational relations and rational relations, the complexity is still the same, like kx time complete. It's only in the last case with transitive Euclidean and numerical relations, it's no longer 2x time complete, but it becomes non-elementary, but not in the total nesting depths, only in the alternation depths between different relations. Then you can also mix these two quantifiers in some restrained fashion. So you obtain something that is still decidable if every time you use such a strict quantifier, it must be associated to a recognizable relation to fall in the decidable fragment. Of course, the others can be any rational relation. And you cannot have a strict quantifier in the scope of a full quantifier. Well, at least if you have that, we don't know if we can deal with that or not. But we know that if it's not the case, then we can decide. Because then you can just do the power set construction as we did. You remove all the full quantifiers, and then you end up with an instance of the decidable fragment of strictly uniform strategy. Then you can get some results from these ones. You can apply them to some other domains, like for example, model checking epistemic temporal logics. For example, CTL star KN. It was known to be decidable for memoryless relations, a perfect recall, asynchronous. It was more or less known also for a perfect recall asynchronous. And now we know that it's decidable and non-elementary for all rational relations, because you can easily encode it into a game where you have just one player. And like player 1 doesn't play, player 2 simulates all the runs of the system. And it's also, so also in dynamic epistemic logics, but I don't have time to explain about this, but for those who know, you can transform the problems of epistemic planning and some notions of epistemic protocol synthesis into this framework, and then apply automata techniques to this kind of problems, which was not like usually done in this community, like automata techniques in dynamic epistemic logics. But so it can give new results also in this domain. So to sum up, for strict uniformity, so it's undecidable for rational relations and even with the synchronous and equivalence. But it's decidable for recognizable relations. For full uniformity, it's decidable for all rational relations, and we have well, I say optimal because you cannot find a class for which the complexity will be better, because it's already 2x time hard without any quantifier. because solving LTL games is 2x time complete. So optimal is in the sense that there is no class of relations for which the complexity is lower. But maybe there is a bigger class for which the complexity is the same. We can generalize to n relations quite easily, and all the decision procedures we have, they can synthesize regular uniform strategy whenever there is one. Because we use automata techniques, and it's classic that you can synthesize a regular tree in the language when it's not empty. So recognizable relations, intuitively, because they are recognized by a finite state automaton that reads a word and then another word and then decides. It means that it only considers a bounded information on each word. So if you want to see that as relation for epistemic agents, it corresponds to agents having bounded memory. So it's not really surprising that it's decidable then, because with bounded memory you can do power set constructions, etc. But then with this automata technique you can easily solve like games with like several players with bounded memory, imperfect information, and epistemic objectives. And but on this I'm not sure exactly what results are known, but well, with these techniques you can do that. And as future work, so it would be nice to have a bigger class of relations for which we have decidability for strict uniformity. So a bigger class of relations for which we can decide the emptiness of jumping automata. We would like to be able to quantify our uniform strategies inside the language, because for the moment it's just at the level of the decision problem. Like, is there a strategy such that? It would be nice to do like an ATL and put this in the language and see what happens. Maybe also, well, here it's written LTL because before we only considered LTL. Now we switched to CTL star, but anyway, it could be nice to see if we can do the same with mu calculus also. Maybe see if there is a strict correspondence between jumping automata and epistemic mu calculus or something like that. And also what I would like to look at now is with information set automata, so this automata that computes information sets for arbitrary rational relations, I'd like to see if you can generalize the classic power set construction for games with imperfect information and see what assumptions you have to make on the what are the least assumptions you have to make on the relations so that the power set construction works. So maybe it would give insights on what are the minimal requirements on the player's abilities for having a power set construction that works. And maybe it can help start to study general classes of games with imperfect recall, but with unbounded memory, imperfect recall.